our textbook, chapter 5, kind of there are a few sections here. But here I like to put this one as a standalone, I would say in my lecture notes, standalone chapters here. And stability basically saying is this. So if we consider a system, an open loop system, and this open loop system is taking up a certain command input. And also the system has its own initial conditions. Okay, so basically we know the initial conditions through the systems will coming into Y transient. Okay, and then for the input, that will go to the steady state response. And the systems basically we put together, and that is equal to our output. Okay, we take summation of the two things together, and that is equal to our output. So basically, output is determined by two things: initial conditions and the input here. So let me label it if this is Rs, and if the output is Ys. Okay. So in terms of our transfer functions, our transfer functions is defined by assuming the initial conditions equal to 0. We don't consider the influence of the initial conditions. So basic transfer function is Y of S and over R, and under the conditions, initial conditions equal to 0. Okay. So that is what we have done so far about we emphasize on this, the input-output relation, and most of the time we don't consider initial conditions in the S domain, in the transfer functions. And now we talk about the stability. Stability basically is these things. And what is the stability? A system, I would say, in more specific control systems. Okay, so if the system is an open loop system without anything, it's nothing to say. It's ugly, it's pretty, has been doomed when the system's but the system can be revised and when we put into the configuration of the control systems here. So here we usually talk about the control system. So here mean the control system, that means under certain controller design, we talk about stability, and then here we can talk about the definition. What is stability? Stability of the system basically is this. If we have okay, so here is the initial conditions, and here is our command. If we have a finite, and this is our output. If we have the bounded command, and initial conditions is always bounded, so let me emphasize here as well. If we have a bounded command, bounded input, bounded, that means the value is finite, the value is a reasonable magnitude or range. Then after this system be operated, if we can expect the output is bounded as well. So that means we consider bounded inputs and inputs in terms of command, in terms of initial conditions. Then if the output is also bounded, then we say the system is stable. Okay, that means the signal in terms of the command 1 or in terms of the initial conditions, the two signals after operated by the system won't be magnified to diverge, then we say the system is stable. Stable, that means it will magnify it will magnify the signals to infinity. That's called a stable system. Okay, so that is a fundamental concept here. And so basically here we put a stable input, stable output in the systems. And we could have bounded input, bounded output system. Okay, so if the input is bounded, then the output is bounded, then the system is stable. And here we have a few more precise classifications of the stability. So here, let me talk about is there's a few categories. Okay, the first one is we call the zero input. Stability. Zero input stability, that means we're assuming we don't consider the influence of command. We only consider the influence of the initial conditions. And from there, we can purely see the systems, the features here. And the second one we're going to talk about is okay. So the characteristic equations basically is the denominators of the transfer functions. So I would say the second category is more toward the output input, more toward using the transfer function as a base. Okay, so this is a very rough the categories. So let me talk about this one. The zero input stability. And in these sections, and here is to build up people more quantitative analysis, the method. Okay, so this section is adding on my own notes, and actually this some of the contents in this section is from the system dynamics, and which is not covered in our textbook. So here you just listen, and here is more qualitative. Okay, more qualitative the things. So the zero input, and that means here we the command input is not considered, and only consider the initial conditions. Okay, and here I want to use okay, so what is a state space? And let me give you a quick introductions. The fundamental, the state space, the most simple one is two-dimensional. For example, here we have x1, we have x2. And for example, if the system has two states, which means the system's dynamics can be completely categorized by two independent variables, x1, x2. Okay, so that one is the most easily visualized in the whiteboard here. And also we could have the 3 states, which means they form into the 3-dimensional. And depends on the degrees of the systems, and we might be able to use, we might need to use n state, which means n states and number of n of the state variables here. But here in visualization, we can use this one for example here. Okay, so the example is this. So for example here, if we have initial conditions, and so say for example here for let me use this example here. So say x double dot plus 2x dot plus 3x equal to say here we consider 0 inputs, so that is null for external force. And let me say x 0 equal to 1 and x dot 0 equal to say 2 here. So that is our initial conditions here. Okay, and again we don't discuss the state space method, and this could be the only sections I'm going to talk about that one. You just listen. So usually from here we can convert these equations into state equations. Okay, state equation is doing this. We simply define the states. And again, don't worry, here I quickly go over and show you how that can work. And the states of the system. And we started from here. This is the second order system. And so we define the state from the lowest one and lowest order, which is 0, and then higher until the one order is smaller than the highest one. So we define the state. For example, y, we define the state and using the y1, okay? So let me define y1, that is the first state, and that's starting from the lowest order, which is x. And then we continue to define the y2 equal to the higher orders, which is x dot, and until we reach the degree, the order that is 1 order less than the highest one, this is 2. So we stop here. Okay, so for example, if this system is a third order, then we would have one more state to define. Okay, so we stop here. So now then here we define this one, then here we take derivative of the state. So that means you can see y1 dot basically equal to x dot, and x dot in turn equal to y2, and y2 dot equal to x double dot from here double dot, and double dot from our equation you can see basically that is equal to minus 3x minus 2x dot, right? I simply move the 2 terms on the right hand side, and that is x double dot. And right now we have the state defined for each of these. So basically that is minus 3y1 minus 2y2, right? Okay, don't worry, you just listen here. This won't be for your learning, but this won't be tested. Okay, so now with this one, you can see basically, let me summarize from here, y1. Basically, we can relate the dynamics of the states into themselves, y2, and y2 dot equal to minus 3y1 minus 2y2. So this is called the state equations. State equation is a combination of the first order differential equations composed of the state variables only. Got it? Okay. So from here, then you can see basically, let me write up into the matrix form. I want you to write it up as d dt of the states y1, y2 equal to the combinations of the states y1, y2, and plus whatever the output here, whatever the input here, we don't have input, we only have this one. So let me do this one. y1 dot equal to y2, so the first equation is y1 dot equal to y2, so that is this row multiplied with this column must equal to y2. So that is the first one is 0, and this one is 1, right? Then the second one, the second equation, y2 dot, that is about this equation. So the two numbers multiplied with this one must equal to this. So basically this number is -3, this is -2. Okay, so that is called the state equations. And state equation in this way, you can see that is the multiplication of the vectors, which is derivative, and together with a constant matrix A, and multiply with a vector. So usually for the state space analysis in controls, we directly get in going into the linear algebra, using eigenvalue, eigenfunctions as a mathematical tools to get into the controller design. So from here you can feel that is a standalone topic, a huge topic, and we wouldn't be able to do it in the fundamental one. But anyhow, right now the people have the concept we can always convert a dynamical systems in a similar way to certain expression like this. Okay, so now the remaining is this with the initial conditions. Initial conditions is y1, 0, y2, 0, equal to, by definition, y1 is the x, so that is 1. And y2 is velocity, and which is 2. So from here you can see this is the combination of the first order differential equations, and they have their own initial conditions. So in theory, we can solve for y1t and y2t. How to solve for it? And again, that is the state space. The equation we don't bother that one here. But in theory, we can do that one. So if we can solve for y1t, y2t, for example, then we will be able to plot the trajectory. Okay. For example, let's say for this example, y1. So let me say the state is y1, the state is y2, and using that example, our initial state is 1 and 2, so basically it's 1, 2, 2 here. So that is our initial conditions here. Okay, so if we will be able to plot the trajectory, then that trajectory could be something like this. So that means this is we plot the yt. Okay, so here I kind of making the schematic. So some systems could be something like this. Okay, so that is the case one, depends on the system dynamics. And so that means for this case, you can see this, when time goes by, the mapping of the trajectory on the state space basically is kind of confined in the range of the limited value. But for this case, it won't converge, won't go into 0 here. So basically here I would say the dynamics of the system is confined within a certain bounded range. Okay, and another possible dynamics could be like this. So say this is y1, this is y2, and this is the initial conditions. And the dynamics, by tracing the y1, y2, it will be gradually come into 0 here. Actually, this will be the case of we did here. Okay, so when time goes by, dt is increasing, so that is the one here. So eventually, the system will converge, the dynamics will converge to 0. And the case 3 will be something like this, y1 and y2. The case 3 will be something like this. So say if this is the initial conditions, its dynamics could be something like this. Something like this. And if we have initial conditions 1, it was starting from here. If we have initial conditions 2, So say if our initial condition, say this time is from inside here, and say that system, that particular system could be dynamics, could be something like this. Okay, so basically for the features of this system, basically its dynamics, it will eventually convert to a cycle, and that one. Okay, so here we can define the categories. For the case one, is we simply call the system a stable system. The stable system, that means is the dynamics won't diverge. It's confined in the bounded regions. We call it stable. For this one, the dynamics eventually converge to zero. So we expect this system eventually will have no displacement, no velocity at its eventual state. So this is called asymptotically. Asymptotic. Okay. For these systems, its dynamics eventually converge into, let me schematic drawing here, converge into a limit cycle. Basically, that is the range where the system's dynamics will eventually going into in the state space. Okay, so this is called a limit cycle. Okay, the limit cycle is also converted to a special case of the stable system. Okay, and so usually most of the times the system dynamics, the stability of the system dynamics can be classified into the three systems. Okay, and for most of our exercise problems in fundamental control theory in ME 409. Is like this system, and this system is belonging to this one. Eventually, the system will get there. Okay, assuming we don't consider any friction model, any dry friction, any coolant friction, then the system will eventually go to here like this. Okay. So here we understand.